Hi, I'm Chris Brown, and this is Module 2.9, an intermediate axiomatic design for axiomatic design and manufacturing processes, also for a standalone course in axiomatic design. So for the next few minutes we're going to be talking about tolerances and the relations between FRs, DPs, and PVs. The objective is to establish continuous tolerancing across the domains from customer to process and to tool. So targets and tolerances. So we're looking at either integral or separate new process or manufacturing process developments. This material can be applied to either. And they should include targets, both target values and tolerances for FRs, DPs, and PVs. There should be defined relations between the elements of the adjacent domains. Now let me remark here too that again we're looking at a part of axiomatic design now that has been recognized as being important but has not been widely used. There's a lot of axiomatic design that can be valuable qualitatively, but sometimes, particularly when we're having more intricate kinds of design problems, it's essential to be quantifying the variables so that, or the elements in the domains. One, it helps us recognize or make better functional requirements, design parameters, and process variables. And it also helps us to come up with a better understanding of the relationships between them and whether or not they're coupled. So let's take a look at the design and manufacture of a mold for a running shoe. So let's zoom in on part of this. So the detail of this, we're looking at the sort of the roughness here in this region. Actually, we could look at a lot of it. Looks so what we're thinking about is how would we make that roughness there. Now, one of the customer needs for the sole pavement interface would be to provide adequate grip for traction. But there's a limit to how much grip you want, and because you have to turn and this shoe has to skid, and if there's too much grip, you're transmitting too many loads to the foot, ankle, and knee. And so you would like some slip for injury avoidance or repetitive motion type, or repetitive sort of impact type things. So let's take a look at the product design. So in the functional domain, we need to provide some friction. And so I'm using mu here as shorthand for friction. And in fact, we could even use this as the friction coefficient. And so the friction coefficient should be between some values of, say, A and B, so that we have enough friction with the pavement, but not too much, so as we might cause some sort of repetitive injury. So A is sort of for grip and B is for slip. So in the physical domain, we might choose RT, and I'm doing this mostly for convenience. This is the peak to valley roughness, and it was introduced a little bit in the last lecture. And so the RT should be between some values. And what we're assuming here, and we'll take a look at it here, is that there is some relationship between the friction coefficient and the RT. And it might look like this. And it might just be a simple line like this. Now this probably would have to be established experimentally. And as far as I know, there aren't any experiments like this, or for the traction on running shoes, although probably there must be some work done in industry. But we've worked here on the friction of tires and pavements. But, all right, in this case, we're going to assume this for the point of illustration of what we want to do. So here is friction A for grip, and so this would correspond to some roughness here, based on this relationship. And here is friction B for slip. So as long as the friction coefficient is in this range, we will have sufficient friction so that we don't slip, and we won't have so much that we start to cause injury. I'm sorry, it'll slip at the right place, and it won't slip at the right place if you want to say that at the other place. And so these two friction coefficients can translate to two roughness parameters, RT, knowing this relationship. So that's the performance tolerance. As long as we're between A and B, we're within the performance tolerance. And there's the roughness of the physical tolerance. So we can see how we can map from performance or functional to physical. In other words, from the performance to the roughness. So let's take a look at the process design. So now we'll start with the design parameter, the physical part. And this is the sole texture RT, which has to be between, say, some limits C and D. Now we'll try ball-end milling, so the step over can define what the roughness is here, and so we'll use our process variable. We'll call this S for step over, and it should be between something like G and H, let's say. So here's the way we would model this. So in the model, we can see that the ball-end mill here, which is looking blue, has a certain radius on it. And as I step over, I leave these peaks and have some RZ value, some peak to height value that will correspond to the step over. Now this kind of surface looks very much like the mold would have to look for the running shoes. So we can write a relationship like this. RZ is going to be about equal to S squared, where S is the step over, times 8, or divided by 8R, where R is the tool nose radius. So in this way we've got actually two parameters that we can use to define RZ, depending on what our particular needs are and how large we might like to step over. So what we would do normally is keep one of these constant and manipulate the other one to get the RZ that we want. Now, those of you who've studied machining may realize that this is very similar to what we have for roughness and turning. And so here's the development for roughness and turning, and you can kind of see where that equation came from. And it's just using the Pythagorean theorem on a triangle like this one, where you've got R is the hypotenuse, F over 2 is one of the legs, and then the other one is going to be the tool nose radius, minus the peak to valley roughness, the RT. So anyway, you can see how that goes, and then you can make an approximation throwing away some higher order terms, and you come up with this classic relationship that's in most of the manufacturing textbooks. If you actually do the experiment, it turns out like, it can turn out like this, so that there is some offset here between the theory and the actual measured roughness as we change the feed and turning. So this points to different ways that we can establish the relationships when we want to know a numeric relationship. One is to run an experiment, and the other is to rely on some theory. So in the same way that we develop the tolerances for the roughness from the friction coefficients, we can also develop the tolerances for the step over from the RT. And so using this relationship, this was the RT axis down here. I'm sorry, this was the step over or feed per revolution axis and turning here. And here's the roughness, on the vertical axis. And so there's the roughness tolerance, and there's the step over tolerance. Now, coupling and tolerance. So we can look at this kind of DP-FR tolerancing that we talked about, or coupling rather, that we talked about in kinds of coupling, or the PV-DP coupling. In other words, lack of independence. When a foreseeable change in the DP or PV will take their corresponding FR and DP out of tolerance. So there is a tendency sometimes when filling in the X's and O's in the matrix to say, there is a dependence here. But is that dependence so large that it will take the other parameter, the corresponding parameter, out of tolerance. So how can you tell when an FR and a DP are coupled? Well, there's theory, and we saw some theoretical development. There's an experiment, and we saw some results of a real experiment and one that was hypothesized. And then consensus. This is sort of the last act of desperation. If you don't have good theory, if you don't have an experiment, and you can't develop the theory or you can't perform the experiment, then sometimes we just rely on consensus. Get all of the engineers who are responsible for it and see if you can get them to agree if there is coupling or not. But if people aren't well informed or understand axiomatic design, they may say, oh yeah, well there is, there can be some variance here based on this other parameter. Well, the question you have to be sure you ask is, will there be enough to take the FR out of tolerance? And if there is, then you need to address it. So metrics and tolerances across the design domain. So the metrics and tolerances in the design and manufacturing processes can improve the power of AD to solve problems. So when we start trying to put the metrics on it, we really begin to increase the power of the sorts of things AD can do, axiomatic design can do significantly. The metrics and tolerances, we should realize, are domain specific, and they can be mapped from domain to domain, as we've seen. Now, metrics for the domains would rely logically, if it's the functional domain, on functional attributes. So you need to measure the way it functions, or have some metric for the way it functions. For the physical domain, it's physical attributes, so you have to be able to measure the physical quantities associated with that product. And in the process domain, how do we tolerance this? And for this, we could look at energy utilization and see how good the energy utilization is, or how if the energy is being brought to bear on something that is that goes back to a customer need and creates value. Thank you for your attention.